Lesson 2.6, and probabilities. Our objective for this lesson is to be able to find the and probability, or joint probability, for independent events and dependent events. Let's start by defining some terms. Our first definition is and probability, also known as joint probability. It's the likelihood of two or more events occurring together. So what we're doing now is starting to combine probabilities. For example, if we know the probability of event A and we know the probability of event B, and probability tells us the probability of event A and B both occurring. In order to calculate and probability, we need to know whether or not the events are independent or dependent. Two events are independent if the occurrence of one event does not affect the probability of the other event. So for example, if I'm flipping coins, flipping a heads on one flip doesn't impact whether or not I'm going to get a heads or tails on the next flip. Those events are independent because one event doesn't affect the probability of a subsequent event. Dependent events, on the other hand, two events are dependent if the occurrence of one event does affect the probability of the other event. So for example, if I'm drawing cards out of a deck of cards, the initial probability of me drawing an ace is 4 out of 52 because there are 4 aces in a deck of 52 cards. But now that I've drawn that ace, unless I put it back, there are now fewer aces in the deck. So the probability of me drawing a second ace would be 3 out of 51 because there's now only 51 cards in the deck and there's only 3 aces left. All right, to calculate and probability for independent events, we're going to, the probability of A and B is going to be equal to the probability of A times the probability of B. So all we're doing here for and probability is we're multiplying the two probabilities for independent events. So if the probability of one event is 1/2 and the probability of the second event is 1/4, then the probability of both of those events happening would be 1/2 times 1/4, or 1/8. All right, now to calculate and probability for dependent events, that's going to be the same thing. We're going to multiply them together, but we have to figure in the change in the probability because of the one event affecting the other. So the probability of A and B is going to be equal to the probability of A times the probability of B given that A has occurred. So let's look at a couple of examples of calculating and probability for independent and dependent events. Our first example is to find the probability of flipping a fair coin 3 times and getting 3 tails. So the first thing we need to determine when we're calculating and probability is whether the events are independent or dependent. In other words, does flipping a coin once affect what's going to happen the next time you flip a coin? And it doesn't, because anytime I flip a coin, the probability of getting a tails or the probability of getting a heads is going to be 1/2, regardless of what happened before. So these are independent events, which means that all we have to do is multiply the probability for each of the events to get the and probability. So the probability of getting a tails if I flip a coin once is going to be 1/2. And then we're going to multiply that by the probability of getting tails on the second flip. That's also going to be 1/2. And similarly, it's going to be 1/2 for the third event. And so 1/2 times 1/2 times 1/2 is 1/8. So the probability of flipping a fair coin 3 times and getting 3 tails is going to be 1/8. For our second example, we're asked to find the probability of drawing 3 cards from a standard 52 card deck without replacing the cards after each draw and getting 3 jacks. So the first thing we need to do again is to determine whether these are independent or dependent events. Well, here, because we're not replacing the cards after we've drawn them, drawing one card does affect the probability of drawing the second card because there are fewer cards in the deck for that second and third draw. So if we had replaced the cards and shuffled them, then these would be independent events. But since we're not replacing the cards, these are dependent events. So the probability is going to be the probability of the first one, of drawing the first card, times the probability of drawing a second jack, given that we've already drawn a jack, times the probability of drawing a jack, given that we've already drawn 2 jacks. So the first probability is going to be 4 out of 52. There are 4 jacks in the deck when we start out of the 52 cards in the deck. So we have a 4 out of 52 or 1 out of 13 chance of getting a jack on our first draw. Then we're going to multiply that by the probability of getting a jack on the second draw. Well, now there's not 52 cards in the deck. There's 51 cards in that deck. And there's no longer 4 jacks, there's only 3 jacks left. And then for the third draw, there's only 2 jacks because we've drawn a jack in each of these first 2 draws. And so if we've drawn a jack the first time, we drew a jack the second time, by the third jack, there's only 2 jacks left by the third draw, there's only 2 jacks left. And that's out of 50 total cards in the deck that are left for that third draw. All right, now we multiply these together. We multiply the denominators. 4 times 3 is 12, times 2 is 24. 52 times 51 is 2,652. Times 50 is 100. What did I say? 2,652. This is so times 50 is going to be 132,600. And this does. We can simplify this. 24 divided by 133,600 is going to reduce to 1 over 5,525. So the probability of drawing 3 jacks out of a deck of cards in a row is going to be 1 out of 5,525.